Hello, and welcome to the Science of Sleep, where questions are welcome, even if the answers slip away like mist between your fingers. Tonight, the universe isn't a machine, it's a whisper, a shimmer, a soft wave beneath your thoughts. You don't have to hold on to anything. Not definitions, not logic, not even certainty. Just drift. Let me carry the weight of confusion for you. All you need is breath. Close your eyes, if they're not already. Now imagine this. The smallest possible thing, tinier than a speck of dust, smaller than a cell, smaller than the nucleus of an atom. Imagine it dancing. Not spinning like a ballerina, but blinking, appearing, disappearing, reappearing somewhere else, like it's shy, or playing a cosmic game of peekaboo. That's where we begin. At the edge of what's real and what's maybe, at the trembling line between existence and nothing at all. We call it the quantum realm, and it doesn't make sense. Not in the way a chair makes sense, or a calendar, or breakfast. Quantum physics is where logic takes its socks off, lays down on a bed made of probability, and mumbles, "Yeah, maybe." You've grown up in a world that works on rules. Push the door, it opens. Drop a spoon, it falls. Say something awkward, and yep, you replay it at 2 a.m. for the rest of your life. But zoom in, deeper, past the skin, past the cells, past the atoms. There, in the flickering basement of matter, the rules break down. Sometimes the spoon isn't really there until it's measured. Sometimes it's in two places. Sometimes it's a wave of possibility. And sometimes it's a thing. And if you're starting to feel a little dizzy, good. That means the story has started to work. Because the quantum world doesn't ask to be understood. It asks to be noticed, gently, like the way you notice a dream while you're still half asleep. We didn't always know this. For a long time, science thought everything was made of solid, measurable stuff. Newton's apple, forces, mass, motion, and it worked. Worked beautifully. You could shoot rockets, build bridges, even predict eclipses. The universe was a well-oiled watch, ticking away. But around the early 1900 second, a few things started acting up. Like electrons not moving in smooth, classical orbits, but instead jumping unpredictably. Like light acting like a wave, and then surprise, like a particle. Imagine asking someone, "Are you a cat or a dog?" And they reply, "Yes." That's what the universe started doing. And at first, scientists hated it. The great Einstein himself muttered, "God does not play dice." And yet, the dice kept rolling. The more we tested, the more we realized. Reality, at the smallest scale, wasn't behaving like it was supposed to. And here's the twist. Even when things didn't make sense, the math still worked. The predictions were flawless. You could calculate outcomes with terrifying accuracy while still having no clue what the heck was actually going on. Welcome to quantum physics, where the rules are slippery, the players are shadows, and nothing is certain, but everything still somehow works. Now, don't worry about equations. No one here is going to quiz you on Schrödinger's constant or Planck's little h-bar. That's not what this is for. This is about the feeling of it all. The way it bends your thoughts just enough to open a space in your mind, not for answers, but for wonder. You'll hear terms like superposition, entanglement, wave function, tunneling, but think of them like flavors in a strange dream. You don't need to memorize them, just notice the taste. Tonight you're going to float through one of the strangest landscapes science has ever discovered. A place where particles don't commit, where cause and effect sometimes break up and see other people, where observation changes reality. And you are welcome here, not as a scientist, not as a student, just as someone curious enough to wonder, wait, did that just happen? Maybe it did. Maybe it didn't. Maybe it's happening right now, in another version of you who already fell asleep and is dreaming of this very sentence. That's the mood we're aiming for. And just to keep things warm, if you find this video strange, comforting, or quietly rebellious, maybe leave a like, or whisper it to someone who needs a voice to fall asleep with. That helps more than you know. Let me leave you with an image. Imagine the whole universe is a field of grass. Every blade is a probability. Every gust of wind is a measurement. And somewhere in that grass, a particle twitches not because it was told to, but because you thought about looking. And then it becomes real. That's where we begin. There's something innocent about shining a light through two little slits in a barrier. It feels like science at its most childlike. A flashlight, a wall, a couple of holes. Simple stuff, right? But this is where reality starts to misbehave. You picture it clearly. A particle, say, an electron fired at a barrier with two openings. It should go through one slit or the other, just like you walk through one doorway, not both. And yet, that's not what happens. On the other side of the slits, we place a screen, and when enough electrons hit it, they don't form two clumps like marbles fired through holes. They form an interference pattern, the kind of wavy pattern you'd expect if they were ripples, overlapping, interfering, creating bands of light and dark. Wait, what? We saw particle. Little bits. And they behaved like waves. Okay, fine. Let's peek. Let's set up a detector to watch which slit they actually go through. And now, the pattern vanishes. The electrons suddenly behave like particles again. No more wave pattern, no more interference. Just two neat piles, one behind each slit, like obedient marbles. As if the electrons knew they were being watched and decided to behave more politely. This is the infamous double-slit experiment, and it's the crack in the wall of classical reality. No matter how many times you repeat it, the result is the same. If you don't look, the particle behaves like a wave. If you do look, it acts like a particle. You might be thinking, okay, so the detector must be changing the particle. But here's the thing. It doesn't even need to physically touch the particle. Just the presence of information, the mere possibility of knowing the path, is enough to collapse the wave-like behavior. It's like asking someone what they were thinking and watching their face suddenly tighten. You didn't change their thoughts, but you changed the conditions under which they can freely exist. What is it about observation that collapses a probability into a fact? And here's the part that keeps physicists up at night. The electron seems to go through both slits when unobserved, as if it exists in multiple paths at once, a ghost of possibilities, exploring all options, only choosing a definite story when someone's paying attention. Now imagine you're one of those electrons. You're headed toward the barrier. Two slits. No one's watching. You feel a little wild, a little wavy, so you split. Or shimmer. You try both paths. You interfere with yourself. You become a pattern of maybe, but suddenly, someone looks, and just like that you choose. One slit, one path, one outcome, and everything else collapses, as if it never was. The wild part is, this isn't just a spooky philosophical idea. This is measurable, reproducible. You can do it with electrons, photons, even whole molecules. And the larger the object, the harder it is to maintain that spooky in-between state. But the principle holds. When not watched, the universe behaves like potential. When watched, it picks a side. You might say, well, that's just how particles are. They're unpredictable. But unpredictability isn't the same as conditional identity. This isn't a coin flip. This is a coin that's in every possible rotation until someone opens their hand. And that opens a quiet little door to a haunting idea. Maybe the universe doesn't commit to reality until something or someone makes it. So what's observing what? Is it the eye of a physicist? The sensor on a lab bench? Or something deeper, consciousness, awareness, a cosmic attention field gently folding the waveform into a story? Even now, the question is debated. Some argue that observation doesn't mean consciousness, just any interaction with the environment. Others suggest that awareness plays a central role, that the observer is more than just a lab tool. But we're not here to argue. We're here to float, to notice. So let's try this. Picture the particle as a daydream. It flutters, unformed, delicate. It could be anything, a raindrop, a kiss, a door left open. But the moment you name it, that's an electron, it collapses into a shape you can measure, point to, write down. And in that naming, the dream dissolves. Maybe that's what science is, a way of pinning dreams down long enough to look at them. And in quantum physics, we've found the limits of the pin. Remember, this isn't just poetic, it's real. The double-slit experiment works. It has rules, math, consequences. Entire technologies like quantum cryptography and potential future computers depend on this bizarre logic. And yet, we still don't know why. It's as if we found the footprints of a ghost that makes predictions better than any model we've ever built, but refuses to show us its face. And it all started with 2 slits. A simple choice. Left, right, or both, or neither, until you looked. Let me leave you with something soft to fall into. Imagine you're standing on the shore, skipping stones. Each stone is a question. Will it bounce once? Twice? And you never know until it lands. But in the space between throw and splash, the stone is every bounce, every splash, every possible future. And maybe that's the universe. A smooth hand, a curious throw, and all the answers shimmering on the surface. Until they touch the water. Light is slippery. You know it well, sunlight on your skin, the glow of a phone screen in the dark, the shimmer of headlights through the rain. It feels so familiar, so obedient, like a wave, rippling outward in soft, predictable pulses. But then you zoom in, and light betrays you. Sometimes, light behaves like a wave. It bends, diffracts, and interferes like a ripple in a pond. Other times, it shows up in tight little packets, particles called photons delivering energy, like polite little messengers knocking one at a time. So which is it? Wave or particle? The answer is maddening. It's both, and neither. And sometimes it depends on how you ask. Back in the early 1800s, a guy named Thomas Young demonstrated that light interferes like a wave. Remember that double-slit business? He did it with sunlight. The result was clear. Interference fringes. Waves were the logical answer. But then came the photoelectric effect, a pesky problem where light knocked electrons off metal surfaces in ways that only made sense if light came in chunks. No matter how intense the light, if the frequency wasn't high enough, nothing happened. Yet a dim beam of high-frequency light? Zap! Electrons danced loose. Einstein explained it. Light had quanta-small, indivisible bundles of energy. He called them photons, and they behaved like particles. So, light is a wave, and also a particle. It doesn't switch, it just is both. But here's where it gets weirder. Not just light, electrons too, and protons, and neutrons, everything, even things you normally think of as solid stuff matter, has this wave-particle duality. Yes, even you. On paper, your body has a wavelength, a really, really small one, because you're so massive compared to an electron, but it's there, just mathematically insignificant. Unless you suddenly become microscopic and well-rested, your wave function is kind of boring. But the electrons in your nerves, the photons in your eyes, they surf this wave-particle weirdness all the time. It's not just a cute metaphor. Wave-particle duality is baked into the heart of reality. In fact, it's built into one of the most important equations in all of physics, Schrödinger's equation. Think of it like this. Instead of a particle having a definite position, it has a wave function, a mathematical description of all the places it could be, with different probabilities. That wave spreads out, and only when you observe it does the wave collapse into a particular location. So the particle is everywhere, and then it's there. It's not indecisive, it's quantum. Let's try a picture. You're at a sushi bar. The chef hands you a menu, but the fish isn't picked yet. It's not tuna, not salmon. It's something, a swirling superposition of options. And then you point and say, that one. And bam, it's salmon. It always was, right? Number. It became salmon when you made the choice. Reality did the same thing. It held all its flavors in potential. And then, by asking, by observing, you pushed it into form. You're not just eating sushi. You're collapsing the wave function of the universe. Now, you might ask, how can anything be both a wave and a particle at once? We don't really know. All we know is that when we measure waves, we see interference. When we measure particles, we get definite locations. And in between, when we're not looking too closely, the universe just hums. It doesn't seem to care about our categories. It doesn't need to choose. It reminds me of a joke. Are you a morning person or a night owl? Yes, that's the quantum world. It refuses to commit to your labels. It's fluid, not fickle, uncertain, not untruthful. Some physicists argue we're asking the wrong question, that wave and particle are just our classical metaphors, crutches for thinking. The truth might be neither, or something else entirely. Maybe the quantum object is some third thing, a quan, as some have called it. Something that only looks like a wave or a particle, depending on how we squint. Like trying to describe a jellyfish with the words glass or balloon. You can try, but it's more than that. It pulses, it glows, it exists somewhere in between. And that's how the quantum world operates. In between, in maybe. But if you're feeling a bit untethered good, that's part of the process. Because this is where science stops feeling like a diagram and starts feeling like a poem. You don't solve poetry. You feel it. And the quantum world, for all its math and mystery, feels a little bit like a dream that answers you with another question. What are you really? A body? A mind? A story? A waveform? Isn't it strange how often you act like a wave, moving through the world without a fixed shape, different at home, at work, at 3 a.m. in the kitchen looking for pickles, collapsing into a solid version of yourself only when someone looks directly at you, and even then, only briefly. Let me leave you with this. Imagine a hallway filled with mirrors. You walk through, and you are particle, but reflected infinitely, you are wave. Each step you take echoes as probability, and somewhere deep in the shimmer, you are more than solid. You are possibility. So sleep well, wave being. You'll collapse into form again in the morning. Let's talk about cats. Not in a cozy, curled up on the windowsill kind of way. In a box, uncertain, maybe alive, maybe not. This is where things get legendary. You've likely heard the name Schrodinger's cat, a thought experiment so famously weird that it's crossed from physics into pop culture, t-shirts and TikTok memes. But if you're still wondering what the fuss is about, or if the cat is okay, don't worry. The cat's fate is symbolic. And it's also your entry into one of the strangest corners of the quantum world, superposition. So what is superposition? In the quantum realm, particles don't exist in one clear state. They exist in all possible states at once, until something collapses the wave function and chooses an outcome. Up and down, here and there. Both and neither. You can think of a particle like a chord on a piano, not one key, a blend of many notes at once, until the moment you press play and the universe picks a single sound. Now, Schrödinger wanted to poke fun at how absurd this sounded, so he imagined a cat locked in a box with a diabolical setup, a sealed container of poison, a Geiger counter to detect radioactive decay, a tiny bit of radioactive material which may or may not decay during the experiment. If the atom decays, the counter detects it, triggering the release of poison. If not, the cat lives. But, and here's the kicker, until someone opens the box, the atom is in a superposition of decayed and not decayed, which means the cat is, what? Both alive and dead? Sort of. But really, the cat is entangled with the system. It reflects the quantum uncertainty at a macroscopic level. It's not about feline suffering. It's about how weird quantum behavior might scale up to the world we know. Now don't worry, the cat's fine. No actual cats were harmed in the making of quantum mechanics. But the point lingers like a smudge on glass. If tiny particles can be in multiple states, why not bigger things? Why not you? Of course, in daily life, we don't see people walking around in ghost states of maybe. You don't bump into your friend and say, oh, you're both at work and at yoga, makes sense. But on the quantum level, This is the norm. Before observation, a system exists in a blur, a spread-out cloud of all possibilities, and measurement collapses it into one. So when you're lying in bed, deciding whether to wake up or snooze for 10 more minutes, according to quantum logic, you're briefly in a superposition of both. Now, unfortunately, you can't use this to avoid consequences. You can't tell your boss, "Sorry, I was in a waveform of attendance." Reality expects a choice. But deep down, at the tiniest level, the universe resists commitment. Here's something spooky. Scientists have created real-life superpositions with actual particles, atoms, even molecules. They've trapped them in states where they're in two places at once, like a coin spinning endlessly in the air, never landing. They've even done experiments with macroscopic mechanical systems cooled down to near absolute zero, where movement becomes quantized, and even those have shown signs of superposition. It's like catching a whisper of magic in a world made of metal and wires. So what keeps us from seeing superposition in everyday life? Decoherence. The moment a quantum system interacts with its environment, air molecules, heat, vibrations, it loses its quantum fog. It chooses a state, or rather, it becomes entangled with so much stuff that the quantum weirdness gets buried under noise. That's why the cat is never really alive and dead. The box leaks information. The system is too tangled up with the world. Still, the lesson remains. Until observed, until measured, quantum systems rest in possibility. And there's something gentle about that, a kind of cosmic patience. No rush to decide, just drifting in the space between maybe and is. There's a quiet metaphor here too. You are always in some kind of superposition. Not quantum, maybe butte personnel, emotional, all the versions of you that might exist, depending on what you choose. The brave one, the tired one, the one who forgives, the one who walks away, and you collapse into one every morning. With every word, every breath, you're not fixed, you're unfolding. Let me give you an image. A bird sits on a wire in early fog. To the eye, it's still, but in the mist, it might be two birds, or five, or none. Only when the sun cuts through does one bird emerge, sharp and clear. That's superposition. That's you. That's the cat in the box. And you don't have to understand it. Just know this. Sometimes, the universe doesn't pick a path until it absolutely has to. And neither do you. So close your eyes again. Let your thoughts blur into their own gentle wave. Maybe you're dreaming. Maybe you're not. Maybe both. Let's stay with the weirdness just a little longer. Tonight, two particles fall in love. Not in the usual sense, not with flowers or shared playlists, but in a way that even Einstein called spooky. A kind of love that transcends space, that defies distance. That makes you wonder if the universe has a secret phone line. This is quantum entanglement. Here's how it works. Take two particles, electrons, let's say, and let them interact. Let them dance for a moment, spin around each other, share a quantum secret, then pull them apart. You can place one on the moon and keep the other in your coffee mug. Now measure one, and instantly, as if by magic, the other reacts. You measure one to be spinning up, the other is instantly down. You measure left, the other flips right. Not later, not with a delay, immediately. As if they were one thing split across two places. Einstein hated this idea. He didn't like the thought of information traveling faster than light. He called it spooky action at a distance. Oh, because it violated his gut instinct about how the world should behave. And yet experiment after experiment has shown it's real. Entanglement exists, and it's not a glitch or a math trick. It's built into the universe. Now, this doesn't mean you can send messages faster than light. Entanglement doesn't allow for texting across galaxies, because while the particles influence each other, you can't control what result you'll get, only that the other particle's result will be perfectly correlated. But still, the connection is instant, like a cosmic string tying them together through the void. And here's the stranger part. It's not that one particle has a hidden value, waiting to be revealed. It's that neither particle has a defined state until one is measured. Only then do both states crystallize together. Think about that. Two particles, no defined identity. But the moment you look at one, both collapse into a matched pair. It's like opening one glove box and instantly knowing whether the missing glove is left or right, even if the other glove is on Mars. But more than that, it's like the gloves weren't even left or right until the box was opened. And here we are again, with reality hesitating to commit until observed. You might be wondering, okay, but how do they stay connected? What's between them? And the answer is nothing. Not space, not time, not even signal. Entanglement just is. It suggests something deeply unsettling or maybe deeply comforting. The universe isn't made of separate things. It's one giant wave function, subtly entangled with itself. Separation is an illusion that holds up well until it doesn't. And it's not just theoretical. Quantum entanglement is now part of real-world technologies. Quantum encryption, quantum computing, even prototypes of quantum teleportation where information about a particle is transferred from one place to another using entanglement as the channel. It's like the cosmos left as a back door into something deeper than space. So what does this mean for you? Maybe it means that connection isn't limited by distance, that there are bonds in this world that don't weaken with miles, that some part of you, some deep interior wave might be forever entangled with people you've shared moments with, even if they're far, even if they're gone. It's not science's job to tell you that's true, but the math doesn't forbid it. There's a gentleness to this thought, a soft thread of connection in the middle of the night. Maybe you've felt it before. That sudden pang when someone you haven't spoken to in years crosses your mind and a message from them appears moments later. A synchronicity you can't explain. A sense of being felt across the divide. Science won't call it magic, but it will quietly admit, yeah, weirder things have happened. Let me give you an image. Two fireflies in a vast forest. One near your window, one on the other side of the mountain. They flash at the same time not because they see each other, but because something deeper binds their rhythm. That's entanglement, not communication, correlation. The universe winked and they blinked together. So tonight, as you drift, you might imagine all the unseen threads around you, the people who've shaped you, the moments that ripple through time, and how, maybe, somewhere in the cosmic quantum mess, you're still linked. Not by wires, not by logic, but by something too fast, too quiet, too beautiful to measure. Sleep well, quantum heart. You're not alone. So you're lying here, listening, not doing anything in particular, just breathing, floating between thoughts. And still, the universe might be reacting to you. It sounds absurd, doesn't it? That you, right now wrapped in blankets, could have any kind of effect on the tiniest particles in existence. But welcome to quantum physics, where you are an observer, and that makes you strangely powerful. Let's not get carried away. You're not bending spoons or shifting timelines with your mood, at least not yet. But the act of observing, of measuring, plays a starring role in how reality unfolds at the smallest level. Let's go back to our friend, the wave function. You remember how a particle doesn't have a fixed state until it's measured? Before that, it's a smear of probabilities, a blur of maybes. Now, measurement collapses that wave function. It takes the potential and picks a path. And the wild part is, what counts as measurement is surprisingly fuzzy. It doesn't have to be a scientist in a lab coat with a clipboard. It could be a photon bouncing off a mirror, or a stray molecule brushing against another. It could even be, maybe, possibly you, your awareness. This has led to some bold speculation over the years. What if consciousness itself causes collapse? What if awareness is the click that locks reality into form? Some interpretations flirt with the idea. The von Neumann-Wigner interpretation even suggests mind plays a fundamental role in deciding the outcome of quantum events. That's a pretty heady claim, It's also not something we can test directly, but it does invite a softer question. What is the role of attention in reality? Because attention isn't passive, it's directional, intentional. It lights up certain corners while leaving others in shadow. And maybe, just maybe, that metaphor carries all the way down to the atomic level. Maybe the universe itself is shaped by where we place our awareness. Or maybe not. But either way, you are always observing, even when you're asleep. Even now. Here's something lovely. A particle's state doesn't exist in any real sense until measured. But once it's measured, its entire history retroactively collapses into something definite. Think about that. The present determines the past. It's like writing a story, then deciding the ending, and suddenly, the entire narrative reorganizes itself to match. We usually think of time as flowing forward, but quantum physics isn't always so obedient. Some equations are time-symmetric. They don't care which way time moves. They allow for effects that seem to ripple backward, as if the future has a say in the past. And this isn't just philosophy. There are experiments like the delayed choice quantum eraser that suggest what we choose to measure now can affect how a particle behaved before it was measured. Let that settle in. A decision made after an event can determine what that event actually was. Again, no time travel, no paradoxes, just a deeply unsettling truth. The universe waits for a story to commit to, and sometimes you are the one telling it. Maybe not with your will, but with your gaze, with your existence. Now, don't worry, this doesn't mean you're responsible for collapsing every electron's wave function in your bedroom. The world is full of observers, photons, air molecules, the floor, but still something changes when we look. Observation makes reality real, not because of belief or magic, but because of how the rules are written. It's like the universe offers you a choose-your-own adventure. Only you don't just pick a page. You make the pages exist. Let me give you an image. You're walking through a foggy forest. The path ahead doesn't exist yet, but each step you take brings the world into being. A stone appears under your foot. A branch materializes overhead, not because they were always there, but because you looked. That's observation. That's quantum physics. That's you. And maybe this helps explain why things feel so strange sometimes. Why the world seems different when you're being watched. Why memories shift. Why silence carries weight. Because maybe observation isn't passive. It's participatory. You're not just watching the show. You're helping write it, frame by frame. So what does that mean here, now? It means that even in stillness, even in sleep, you matter. Not in a grand, save the galaxy kind of way, but in the soft, quantum way, like a flicker that decides which ripple to follow. So breathe in and out. You don't need to do anything. You don't need to choose. The universe is happy to hold your possibilities. You're not behind. You're not late. You're simply observing, and that is enough. Let the particles dance a little longer. They're waiting for your attention. Let's take a breath. By now you've wandered through double slits, shimmering waveforms, cats that are maybe alive, maybe not, and particles dancing in distant pairs. And yet we still haven't answered something quietly important. When does a possibility become real? When does a wave function, this dreamy mathematical cloud of maybe, actually collapse? This brings us to one of the most whispered about moments in all of quantum theory. The collapse of the wave function, a phrase that sounds like a sci-fi doomsday, but is really more like a curtain fall at the end of a scene, a closing gesture, a commitment. The wave function, if you remember, is just a mathy way of saying, this thing could be here, or there, or spinning clockwise, or not at all. But once you measure it, bam, the cloud shrinks, the possibilities vanish. One outcome becomes real, or at least real enough. It's not that the particle traveled through all the options and picked one. It's that all the options existed as pure probability until observation forced a decision. Some physicists say it's like asking the universe a question, and the act of asking collapses all possible answers into one. You could say reality gets stage fright. The weird part is, this collapse isn't explained by the standard equations. It's not in the math. It's just assumed. Something happens when we observe. Something irreversible. A shift from maybes to one definite yes. So what triggers it? A conscious mind? A physical interaction? A camera? No one agrees. And that's the delicious mystery. Now, collapse is often described as instantaneous. The particle's location, spin, or momentum becomes fixed the moment we check. But where does the rest of the wave function go? Was it just an illusion? Some interpretations say, yes, the other possibilities were never real. Others say, hold on, the other options still exist, just not in this universe. We'll get to that when we talk about many worlds. Bring your extra toothbrush. But for now, let's sit with this. You exist in a collapsed reality. Everything around you has already chosen a path. The particles have picked their lanes. The wave functions have settled. You're living in a world of decisions already made. And yet, in the background, the uncollapsed still hum, because collapse is ongoing. It doesn't just happen once, then stop. It's happening everywhere, all the time. Particles are collapsing, wave functions are falling in love with outcomes. 1 trillion tiny curtains falling every second, like a universe constantly choosing who it wants to be. You might imagine this like raindrops on a pond. Each ripple a possibility, then plunk, one forms a splash. Not because it was the right ripple, but because it was touched, observed, measured, known. Collapse is intimacy. It's the moment of contact between potential and presence. Let me give you something gentler. You're sitting by a campfire. The coals glow. The air is still. Somewhere in the dark woods, you hear the rustle of a branch. What was it? A deer? A fox? The wind? You lean in. You squint. You wait. The sound happens again. And now you know. It's a fox. That moment when the possibilities narrowed and one answer landed in your mind, that's collapse. Now expand that to every molecule, every spinning electron, every shadow of an atom waiting to be seen. Collapse isn't an explosion. It's a hush, a sigh in the fabric of the possible. But don't be fooled, collapse is also wildly powerful. It's why you can read this sentence, why your eyes detect photons and send them as electrical pulses to your brain, why you exist in a state that makes sense. Without collapse, nothing is definite. No hands, no rocks, no coffee, just blurry math. Collapse gives reality edges. So what about you? Do you collapse too? In some ways, yes. Every decision you make is a kind of wave function collapse. You could have said yes, but you said no. You could have stayed, but you left. Each choice slices away the maybes. Each action is a narrowing of your own internal waveform. It's comforting to know that indecision is natural, that life itself holds superpositions, until you move, and the world shifts to match. And sometimes, collapsing into one reality means letting go of another. That's not loss, it's how anything becomes real. So, if you feel like you're floating in probabilities tonight, uncertain, unsolid, just breathe. You don't have to collapse yet. The universe is patient. Let me leave you with this. Imagine a sky filled with stars, each one a flicker of what could be. As you lie still, one star brightens, just a little, as if it knows you're watching, as if your gaze gave it permission to shine. That's wave function collapse. That's what makes anything real. That's you, being part of the story. Let's get blurry. Tonight, we land in one of the strangest and most misunderstood corners of quantum physics, a rule so famous it's been stapled to t-shirts, memes, and bad motivational posters. A rule that says, you can't know everything at once. Welcome to the Heisenberg uncertainty principle. It sounds dramatic, but its core is simple. If you know a particle's position very precisely, you cannot know its momentum precisely at the same time, and vice versa. The sharper one gets, the fuzzier the other becomes. Not because your tools are bad, not because your eyes are squinty, but because of how the universe works. Let's try it with something familiar. Imagine trying to catch a fast-moving firefly in the dark. You shine a flashlight to find it, but the light itself nudges the firefly, making it dart off in a new direction. That's kind of what happens when you try to pin down a particle. To see where it is, you have to interact with it, bounce a photon off of it, maybe. But that interaction changes what it's doing. You gain knowledge at the price of disturbing the system. But Heisenberg wasn't just talking about tools. He was talking about reality itself. Position and momentum aren't just hard to know together. They are fundamentally undefined at the same time. The more you know one, the less the other exists in a meaningful way. This isn't a flaw. It's the fabric of the quantum world. And it's not just position and momentum. Other pairs of measurements, like energy and time, have the same tension. They live on opposite ends of the knowledge teeter-totter. You push one down, the other lifts away. Now, this might sound like a cosmic prank, but uncertainty is more than a nuisance. It's what gives the quantum world its flavor, its texture. Without uncertainty, nothing could move. Everything would be frozen in perfect clarity. And perfect clarity is sterile. Motion, energy, warmth, these come from fuzziness. The vacuum of space? That's not a void. It's a foam of uncertainty. Tiny fluctuations pop into and out of existence because of this principle. And this blurry dance is what gives rise to particles, to forces, to you. So next time your plans fall apart or your brain feels foggy, just remember, the universe runs on uncertainty. Without it, there would be no light, nor atoms, nor change, no life. You might think of uncertainty as the engine of possibility, a low hum beneath all outcomes. Here's a silly metaphor. The quantum world is like ordering takeout from a mysterious restaurant. You know the dish is noodles, but until the bag arrives, you can't know how spicy or how tangled or whether there's an unexpected boiled egg hiding inside. And trying to peek, shaking the bag, poking around, just makes the noodles shift around more chaotically. So you just wait and let the mystery deliver. But uncertainty isn't chaos. It has rules. It's predictably unpredictable. There's a limit to how fuzzy things can get. That limit is defined by Planck's constant, a tiny number, but absolute. It's the built-in grain of the universe. Like the pixel resolution of reality, no matter how fancy your microscope, you'll never get past that blur. And that's okay, because the universe isn't blurry out of laziness. It's blurry out of necessity. Now here's where things get oddly personal. Think about how we try to measure people. We ask, where are you now? What are you doing? What's your 5-year plan? But pin down someone too precisely, schedule every minute, predict every mood, and they become unrecognizable, flat, bored, mechanical. Humans, like particles, need room to blur. You can't fully know where someone is and where they're going, because motion needs mystery. And that includes you. You're not just a set of coordinates and speed. You are movement through uncertainty. Your thoughts jump, your heart wavers, your dreams change. And that's not a flaw, that's physics. So next time you feel unsure, unclear, maybe don't fight it. Instead, imagine your mind like a wave packet, a probability cloud, expanding gently into the dark. You don't need to know exactly who you are to be real. Just like the particle, just like the light, just like the universe. Let me leave you with an image. A hummingbird hovers in twilight. You catch a glimpse, wings blurred, body sharp, then gone. You know it was there, but you cannot say where it went or how fast it left. Just that it was, for a moment, beautifully uncertain. So tonight, let your thoughts blur gently at the edges. Don't rush to pin them down. Let your mind become a soft waveform, because in the quantum world, and maybe in yours, clarity isn't always the point. Sometimes the beauty is in the blur. Let's imagine a wall, not a metaphorical wall, an actual one, made of atoms, dense and solid, impenetrable. You knock, and it answers with resistance. Now imagine a particle, say a tiny electron, rolling toward this wall. It doesn't have the energy to climb over. It shouldn't be able to get through. But somehow, it does. No breaking, no smashing, no digging. It just appears on the other side. This is quantum tunneling, and it's as close to magic as physics allows. In the classical world, the one your brain evolved in this makes no sense. If you toss a ball at a hill that's too tall, it rolls back down. It doesn't teleport through the hill. But in the quantum realm, particles aren't little dots, they're waves of probability. And these waves don't stop abruptly at a wall. They leak through, faintly, delicately, like a whisper through a keyhole. And once in a while, when the math allows, that whisper becomes a full-bodied presence on the other side. The particle tunnels. It didn't go over. It didn't break anything. It just skipped the rules. From one point of view, this is a glitch. From another, it's grace. And it's not just theory, this happens constantly in real life. Quantum tunneling is what allows the sun to shine. No, really. Deep inside the sun, protons positive, repelling each other, need to get close enough to fuse. But the classical energy isn't enough to make that happen. So they tunnel, they cheat the odds, and fusion ignites. Every beam of sunlight on your face is the result of quantum tunneling, and it gets even stranger. Modern electronics like flash memory and semiconductors depend on this phenomenon. Quantum tunneling is a feature, not a bug. It's used in devices, harnessed, as if we've built tools from the logic of dreams. So what does it feel like? Imagine you're on one side of a mountain. You throw a ball toward it, nothing fancy, not too hard. But instead of bouncing back, the ball vanishes. A moment later, it rolls gently down the other side. You didn't break the mountain. The ball didn't burrow. It just wasn't constrained by classical logic. Now you're starting to see how slippery reality can be. Particles act as if they know what could happen, and sometimes act accordingly, even when it seems forbidden. They don't always ask permission. They act on probability. And if there's even a tiny chance, they take it. So what can we learn from this? Well, maybe some walls aren't as solid as they seem. Maybe the limits you think are absolute. The things you say, I could never do, or that's impossible, aren't made of stone. Maybe they're quantum, soft at the edges, leaky, not as final as they pretend to be. Here's something lovely. Tunneling is more likely when the barrier is thin or the particle has high energy. But even a low-energy particle can tunnel through a thick wall. It just takes time and patience. You don't always need force. Sometimes you just need to persist in your waveform, to keep vibrating, to wait for your chance to leak through, and suddenly you're on the other side. In the quantum world, nothing is truly stuck. Every barrier has a probability curve. Every obstacle has a sliver of hope. Let me give you an image. A single candle behind a locked glass case. No door, no key. You reach toward it not with hands, but with light, and slowly your warmth seeps through. Not all at once, just a flicker, a shimmer, a soft transmission through the impossible. That's tunneling. That's hope. That's the way a particle tells the universe, you don't own me. So tonight, if you feel boxed in by thoughts, by limits, by fear, just remember, particles tunnel, stars burn, and walls aren't always walls. Sometimes they're invitations. Sometimes they're lies. Sometimes they're just waiting to be imagined through. So keep vibrating, little particle. Your path might surprise you. Let's drift into nothing. Not the poetic kind of nothing, but the literal, physical nothing. The vacuum, the void, the space between stars, where nothing should exist. Only, it isn't empty. Not really. In quantum physics, even a perfect vacuum isn't truly void. What we think of as nothing is a bubbling foam of virtual particles flickering in and out of existence like whispers you almost hear. They're not real in the usual sense. They can't be isolated or captured. But their effects, oh, they're real, measurable, predictable, necessary. The term is almost mischievous. Virtual particles. They're like quantum ghosts, appearing and vanishing before they can be pinned down, borrowing energy from the vacuum with permission to exist briefly, as long as they repay that energy debt quickly enough to satisfy the uncertainty principle. This isn't just sci-fi. One of the clearest proofs of these invisible fluctuations is the Casimir effect. Imagine two metal plates placed just nanometers apart in a vacuum. Nothing should be between them, right? And yet, they gently push toward each other. Why? Because the vacuum around them isn't really empty, it's filled with fluctuating energy. Outside the plates, more quantum modes can exist. Between the plates, fewer. That imbalance creates pressure. No air, no heat, just the breath of the vacuum itself. Think about that for a moment. Two objects nudged together by nothing. Even stranger, virtual particles help explain why atoms don't collapse, why the electromagnetic force works, why black holes evaporate. Yes, Stephen Hawking showed that particles escaping from the edge of a black hole's event horizon are a consequence of quantum vacuum fluctuations. That's right, black holes, the ultimate everything, suckers, slowly bleed away into nothing because of this not quite nothing. So we ask, what is the vacuum really? It's not an empty room. It's a quantum field, a restless sea of potential. Every particle we know arises from one of these fields. The electron has its field, the photon has one too. Even the famous Higgs boson, just a ripple in the Higgs field. What we call particles are really excitations, tiny tremors in invisible fields that permeate all of space. In this view, the universe is not made of stuff. It's made of fields that ripple, shimmer, and resonate. You are, at your core, a symphony of excitations in overlapping fields, momentarily holding together in the shape of a person. And yet, all of it floats in the vacuum. Even you. There's something deeply humbling about that. Everything we see, the galaxies, the oceans, the breath rising from your chest right now rests on a foundation that appears to be nothing, but is actually the most fundamental thing of all. It makes you wonder, if empty space is so full, what else are we misunderstanding? Maybe the silence in your life isn't empty. Maybe the moments when nothing seems to be happening are when the deepest tremors are stirring beneath the surface. Maybe the pause is not absence but potential. Let's imagine it. You're floating in space. No sound, no stars, no planets. Just dark, infinite, quiet. But beneath the silence, the vacuum trembles. Not in a loud, obvious way, but subtly. Blips of energy pop into existence and vanish before you can blink. A particle, an antiparticle, appear, disappear. Not random, not chaotic. Just statistical kindness built into the fabric of the universe. You're not in a void. You're in a canvas of possibility. And that's how you can think of yourself too. Even when you feel emptied out, tired, lost, still there's a quantum hum beneath your skin. Something vibrant, unfinished, ready to ripple when the moment comes. Let me leave you with this. The deepest nothing isn't blank. It's alive with the unborn. And you, floating now, in thought, in breath, in night, are not drifting through emptiness. You are resting on the richest silence the cosmos has ever known. Let's check into a hotel that shouldn't exist. A hotel where every room is full, but somehow there's always room for one more guest. And when someone leaves, the number of guests doesn't change. Welcome to Heisenberg's hotel, sometimes known as the quantum vacuum, sometimes as a metaphor for the slippery idea of identity at the smallest scale. It's not a real place, of course, but it helps us visualize something almost impossible, the way particles and fields behave when individuality breaks down, where knowing exactly what something is becomes impossible because everything it is depends on what's being measured. The name of the game here is identity blur. In classical physics, objects are distinct. A ball is a ball. It has a size, a position, a mass. You can label it, paint it red, and keep track of it as it moves. But in quantum mechanics, the very idea of this particle versus that particle begins to fray. Let's say you have two electrons. In every classical sense, You'd expect them to be two separate, identifiable objects. But electrons are fundamentally indistinguishable. Not just hard to tell apart, literally impossible. There is no this one and that one. If you swap them, the system behaves as if nothing has changed at all. It's like trying to label raindrops in a cloud. This indistinguishability leads to the strange rules of quantum statistics. Particles that follow Fermi-Dirac statistics, like electrons, can't occupy the same quantum state. This is the Pauli exclusion principle. No two fermions can share the same room, so to speak. That's why matter doesn't collapse into one dense blob. It's why atoms have structure, why your body has volume. Meanwhile, bosons particles like photons play by different rules. They love to pile into the same state. The more, the merrier. That's how lasers work. 1 billion photons, all in lockstep. The same energy, the same direction, like a choir singing a single, perfect note. So this imaginary hotel we spoke of? It has 2 wings. In the Fermion wing, no 2 guests can share a room. If a room is full, newcomers are pushed into higher floors. In the boson wing, guests are more like enthusiastic concert-goers. Everyone crams into the same room. No boundaries, just resonance. And the whole hotel is built inside that same mysterious quantum vacuum, where particles aren't solid tenants, but excitations ripples in a field. They don't exist in the way you exist in your chair. They flicker in and out of identity, surfacing when measured, dissolving when ignored. Which brings us to one of the hardest questions. What makes a particle real? If you can't track it, if you can't label it, if you can't even say which one it is, how can it be said to exist at all? Quantum field theory answers, don't think of particles as things. Think of them as events. Not this electron, but this happening of electronness. It's like saying a flame is not an object, but a process. A condition, a pattern of activity. And that's a far cry from how we experience the world. We're used to nouns, solid things, but in the quantum world, reality leans more toward verbs, less I am, and more I'm currently happening. It gets weirder. In quantum field theory, what we think of as empty space is actually filled with the lowest possible energy, a ground state. But even this state seethes with fluctuations. The fields never sit still. So when we say a particle appears, we really mean a quantum field has hiccuped loud enough for the universe to notice. In this model, you could say the entire universe is one giant hotel lobby of vibrating fields. And what we call particles are just check-ins. Short visits, some stay longer than others, but none are permanent. Even the idea of a vacuum, the lobby itself, isn't stable. Physicists wonder whether our universe is sitting in a false vacuum, a local minimum, a comfy pit of temporary stability. If true, a more stable vacuum could exist elsewhere. And if we ever tunnel into it, and reality as we know it would vanish. Don't worry, it's probably not happening tonight. But still, it leaves a strange impression that everything we know, everything we are, might be resting on a shimmering field, one hiccup away from rewriting the laws of physics. So what do we do with that? Maybe we rest in the uncertainty, except that we're not fixed objects but patterns, and that the rooms we occupy, our roles, our identities, our moods might change, might blur, might disappear and reappear like ripples in a universal pool. Let me leave you with this. Imagine a grand hotel stretching into forever. Some rooms are occupied, some empty, some flicker in and out of reality. You arrive, check in, stay a while. And when you leave, the room doesn't vanish, it just returns to potential. The hotel remains. So sleep gently, fellow traveler. Tonight, you're not a guest, you're a ripple, and the field is holding you. Let's sink below the surface now, beneath the particles, beneath even the atoms and the familiar quantum chaos. Underneath it all is something quieter, more fundamental, fields. This is the world of quantum field theory, or QFT for short. At first glance, it sounds like just another layer of abstraction, maybe a fancier way of talking about electrons and photons and all the usual suspects. But it's more than that. It's a full rewrite of what we thought reality was. In quantum field theory, particles are not the base level of reality. They're not billiard balls, or building blocks, or tiny dots flying through space. They're ripples. Each type of particle, electron, quark, neutrino, photon, is just an excitation of its corresponding field. One field per particle species, and these fields stretch across all of space. They are always there, even in a perfect vacuum, even in you right now. The electron you imagine isn't a little thing flying around. It's a temporary wrinkle in the electron field, the way a wave is just the ocean, rising. You don't see the field itself. You see the wiggle. This is the shift quantum field theory gives us. Particles aren't objects. They're events. The field is the thing. The particle is the twitch. That may sound abstract, but it works better than any other theory we have. It explains electromagnetic forces, the strong and weak nuclear interactions, even the creation and annihilation of particles. It lays the groundwork for the Standard Model, which, despite its ugly math and missing pieces, is the most successful physical theory humanity has ever created. And QFT has teeth. It predicts things like the anomalous magnetic moment of the electron with such absurd precision that we've measured it out to the 12th of December decimal places, and it still agrees. That's not luck. That's something fundamental being tapped. But QFT also humbles us, because it forces us to let go of the idea that space is empty, that particles are things, that anything is solid in the way we once thought. Instead, we begin to see the universe as a tapestry of overlapping fields, endlessly fluctuating, like 1,000 instruments playing beneath the stage, most unheard, some bursting into song just long enough to be noticed before fading again. And you, yes, you are made of these waves. A thrum in the quark field, a pulse in the gluon field, a structure that emerges, briefly, from the haze. Even gravity, though still mysterious in the quantum realm, might one day fit into this field framework if we ever figure out quantum gravity, or a workable theory of everything. Now let's pause and bring it back to Earth. If everything is fields, why do things feel solid? Why doesn't your hand fall through your coffee mug? Why can you type or sip or open a door? Because of the Pauli exclusion principle and the interaction of quantum fields at microscopic levels, fields ripple into each other. Particles resist being in the same place. Electromagnetic repulsion, electron orbitals, and the interplay of fermion fields make your hand bounce off the mug before it can pass through. It's not solidity, it's interaction. It's the illusion of solidity made by resistance. In other words, nothing touches anything. You have never actually touched anything in your life. Not your phone, not your pillow, not even the person you love. It's all fields pushing back. And strangely, there's something comforting in that. If everything is ripple and resistance, then everything is connected too. There's no separate, there's no edge where the self ends and the universe begins. There's just waves, and the way they interfere. Let's bring this into feeling. You walk into a quiet room. You don't move. You barely breathe. But somehow, you feel something. The stillness has shape. The air holds tension. Nothing is said, but everything is present. What you're sensing may not just be mood or psychology. It may be at some absurdly small level the way fields overlap. Your presence isn't just you. It's your field stirring the universal quilt. So, perhaps your thoughts ripple. Perhaps your sadness echoes beyond your skin. Perhaps joy too is not just internal, but field-generated. This isn't science fiction. It's science with room for wonder. Quantum field theory says the universe isn't made of stuff. It's made of behavior. Flickers, patterns, recurrences. It's not, there is a photon. It's, the electromagnetic field wiggled here. And yet those wiggles paint the stars. Let me leave you with this. Close your eyes and picture a calm ocean at night. No wind, no sound, but somewhere far away, a pebble drops. The ripples spread outward silent, steady crossing unseen miles. Now imagine you are that ripple, not the pebble, not the ocean. The ripple, brief, precise, unrepeatable, but deeply, undeniably real. That is quantum field theory. And that is you. Let's return to something that's been quietly bothering us. If the quantum world is so strange, so wavy, so uncertain, so ghost-like, then why does anything feel normal? Why don't chairs behave like probability clouds? Why doesn't your coffee mug tunnel through the table? Why does the world feel solid, predictable, even a little boring most days? Because somewhere along the path from particle to person, from quark to quiche, the strangeness seems to vanish. Quantum behavior just stops showing up. But it doesn't disappear, it just fades. And the reason for that is something soft and slippery and crucial called decoherence. Here's the idea. Quantum systems can exist in superpositions, multiple possible states at once, but only when they are isolated. As soon as a quantum object interacts with its environment, be it air molecules, light, warmth, vibrations, it starts to leak its quantum possibilities into the world, and all that delicate weirdness gets tangled up in everything else. That tangle makes it look like the system has chosen one outcome, even though it hasn't truly collapsed in the conscious observer sense. This is decoherence. It's not observation with a pair of human eyes, it's interaction with the messy world. The wave function doesn't vanish, it just spreads out and blends in, like ink in water. So instead of particles existing in clear superpositions, they get entangled with their environment, and the result is that the weirdness becomes practically invisible. It doesn't disappear in principle. It just becomes impossible to extract. The information is still there, just hopelessly scrambled. Think of it like a violin string vibrating in a vacuum. You'd hear the clear, pure note. Now place it in a noisy room filled with wind and birds and conversations. That note is still being played, but it's buried under layers of other waves. That's what happens to quantum coherence. It's drowned in context. This is why classical physics works so well at the human scale. Why apples fall instead of fuzzing into orbit. Why bridges hold. Why your cat, if observed, is either alive or not. It's not that the quantum rules change. It's that the system becomes too big, too busy, too tangled to keep the strange song going. Now you might ask, is there a way to stop decoherence? The answer is yes, but only in very carefully protected environments. That's what quantum computing tries to do. Preserve coherence long enough to perform calculations that exploit superpositions and entanglement. Quantum bits, or qubits, have to be kept cold, shielded, quiet. A single photon, a stray vibration, can ruin everything. It's like trying to write poetry on a snowflake in a storm. But when it works, it's beautiful. And this is where decoherence becomes more than just a scientific term. It starts to sound a little personal, because you are a system too. You have a wave function in a poetic sense, a set of possible thoughts, actions, dreams, futures. But then comes interaction, nuance, context. You collide with other people, with expectations, with the world, and maybe some of your quantum possibilities decohere. Not because you've failed, but because the environment is messy, and because it's impossible to keep every dream vibrating forever. But, and here's the grace, some quantum states can be preserved longer. Superpositions with structure, protected combinations, balanced states that resist the storm just long enough to do something meaningful. In quantum computing, these are called decoherence-resistant states. In life, maybe we call them moments of clarity, a quiet hour of thought, a conversation that feels untouched by noise, a dream you keep returning to, even when the world gets loud. So, what does decoherence teach us? That the strange quantum world is still here, beneath everything. That reality doesn't switch off weirdness, it just filters it. That your coffee mug, your hand, your breath all still obey quantum laws. They're just soaked in noise. Let me give you an image. You're standing at the edge of a frozen lake. The ice stretches forever. You kneel and press your ear to it. Beneath the surface, you hear music. Faint, delicate, complicated. That's the quantum world, still playing. just muffled beneath the cold certainty of experience. And in the quietest moments, when everything else stops, you might hear a chord or two. So tonight, rest easy knowing this. The world didn't betray its strangeness. It just wrapped it in silence. So you could stand on it. Let's talk about time. Not the kind ticking on your wall or glowing from your phone screen. Not the to-do list kind. The birthday kind. The how late am I kind. We mean quantum time. The deep, weird, rhythmless version. The kind that makes physicists stare out windows for hours. Here's the first strange thing. In most quantum equations, time isn't special. Seriously. In the famous Schrödinger equation, the bedrock of quantum mechanics, time is just a parameter, a background thing. It flows in one direction, not because the math demands it, but because we do, because we expect it. This is unsettling, because in everyday life, time is everything. We experience it moving forward, always forward, from breakfast to bedtime, from cause to effect. But quantum physics doesn't quite play by those rules. Some processes are time-symmetric, meaning if you filmed them and hit rewind, they'd look the same. There's no built-in arrow, no preference for past or future. A particle interacting with another particle doesn't care which side of now it's on. It just follows probabilities. This raises a disturbing question. What if the direction of time is an illusion, one born not from physics but from entropy, from disorder increasing, from the universe tending toward messiness? In thermodynamics, things get messier over time. An ice cube melts, a cup shatters. That gives us a psychological sense of direction, a sense that time moves. But quantum events don't follow this trend so obviously. Some theories even propose that what we call the past and the future are symmetrical branches coexisting in a broader, timeless structure. In fact, there are quantum models where time emerges from entanglement, not as something fundamental, but as a kind of illusion built up from correlations between systems. Like a movie created from still frames, nothing moves but in the right order. It feels alive. So, if time isn't flowing, what is it? Maybe it's context, a way of organizing how events relate to each other, a tool our brains use to stay sane. Or maybe it's an emergent property, something that only exists once there's enough complexity to measure change. Now let's dive into something stranger. There are experiments like the delayed choice quantum eraser that suggest what we decide to measure now can affect how particles behaved in the past. Yes, you read that right. It's as if the particle waited for you to make a choice in the future before finalizing its history. No paradoxes, no time machines, just a reality where cause and effect become fuzzy. It's not that the past changes, it's that the past wasn't definite until the present made it so. Let that sit. In quantum physics, the universe might not write history line by line, it might write in layers, only inking over them once observation commits to a version. And then there's the idea of quantum time loops, proposed in some interpretations of quantum gravity. In these, particles can interact with earlier versions of themselves, creating feedback loops that, if you're not careful, can make your brain slide right off the table. But even without loops, the mere idea that time isn't fundamental changes the story. We're used to thinking of ourselves as travelers, moving from past to future like a car on a road. But maybe we're not moving at all. Maybe we're part of a fixed structure, a space-time tapestry, and what we call now is just the slice our minds happen to be lighting up. It's a shift from I am going through time to I am part of time, and the quantum world might agree. So, what does this mean for you? Maybe it means you're not just a product of your past, that the future isn't something hurtling toward you, but something already woven into the shape of who you are, waiting to unfold. Maybe it means that your presence is bigger than a moment, that somewhere, deep down, parts of you linger in yesterday, while other parts are already whispering into tomorrow. Let me give you an image. Picture a library that stretches beyond sight. Each book a moment in time. They don't fly past you. They surround you. You don't walk from one page to the next. You're already part of the story. And sometimes, just sometimes, you feel it. A memory that returns with clarity, as if it never left. A dream that felt like déjà vu before it even began. A second that stretches, then snaps back. So tonight, rest not in the rush of time, but in the stillness beneath it. Because in the quantum world, time may not pass. It may simply be. Now, let's take all this weirdness, superposition, tunneling, entanglement, decoherence, and do something bold with it. Let's try to compute. This is the dream of quantum computing. To use the rules that make the universe so deeply confusing and turn them into a kind of engine, a machine that doesn't fight uncertainty, but feeds on it. It starts with a bit. In classical computing, a bit is either a 0 or a 1, nothing in between. Every app you've ever used, every cat video, every search, every emoji, just long strings of 0-second and 1-second dancing in silicon. But in a quantum computer, the smallest unit isn't a bit, it's a qubit. And a qubit isn't either 0 or 1, it's both, until it's measured. It exists in a superposition, a blend of possibilities, a ghost of answers. And that tiny difference between definite and maybe changes everything. Because if you have two classical bits, they can be in one of four possible states, 0, 0, 0, 1, 10, or 11. But two qubits, they can be in a superposition of all four at once. Add a third qubit, and now you have a machine exploring 8 possibilities simultaneously. 10 qubits, over 1,000. 20, over 1,000,000. Scale this up, and suddenly you're not just solving one problem, you're solving all possible versions of the problem at the same time. That's the magic. Quantum computers don't compute faster in the classical sense. They don't just run more quickly. They compute differently. They operate in a space of possibilities, letting the quantum system explore paths in parallel before collapsing into the most useful result. It's like trying every key on a massive keyring at once, rather than one by one. But with great possibility comes great fragility. Qubits are delicate. They need to be isolated, kept at temperatures near absolute zero, shielded from the tiniest disturbances. A breath, a photon, even a magnetic fluctuation can cause decoherence, collapse, and ruin the calculation. That's why quantum computers aren't in your laptop. They're in labs, surrounded by elaborate cooling systems and error correction codes. They're prototypes, promises, not yet practical for most everyday tasks. But they're improving. And when they work, they do things that no classical computer on Earth could match, like factoring massive numbers, or simulating molecules for drug discovery, or optimizing complex systems in ways that classical algorithms can't touch. Because at their core, quantum computers are native speakers of quantum mechanics. They don't need to approximate quantum behavior. They are quantum behavior. And that might be the biggest shift of all. Classical computers were built to model the world. Quantum computers are built from its fabric. They're not just calculators, they're participants in a kind of dance with reality. Now, this doesn't mean your phone is going obsolete tomorrow. Quantum computers won't replace classical ones, not for browsing the internet or watching sleepy science videos. Classical computers are still better at many things. Clear, reliable, stable. But quantum computers might change everything behind the curtain. They might help us understand chemistry, which is quantum at its core, or simulate black holes, or unravel the mystery of high-temperature superconductors, or even bring us closer to a theory of quantum gravity. They might solve problems we haven't even learned how to articulate. But maybe the real poetry of quantum computing isn't in the results. It's in the metaphor, because you, too, hold superpositions. You are capable of contradiction, of being calm and chaotic, of holding love and fear in the same breath, of being undecided and yet full of purpose. Quantum computers embrace that ambiguity. They don't collapse until they must. They explore all versions of the story before choosing an ending. Maybe that's a lesson. You don't have to rush your decision. You don't have to know everything right away. You're allowed to explore multiple states of being, and eventually, the right one will emerge. Let me give you an image. A spider spins a web in the morning dew. Each strand is a potential answer. The web vibrates, the wind blows, and when something lands, the whole system responds. That's computation, not as a rigid process, but as a feeling, a resonance, a ripple through possibilities. So tonight, think of your mind as a quantum machine. Let your thoughts drift across options. No rush to collapse, no pressure to compute, just the soft humming of possibilities, waiting for the quiet moment when one becomes real. Now let's follow one of the boldest threads ever pulled from the tangled fabric of quantum mechanics. It starts with a simple question. What happens to all the other possibilities? In every superposition, there are countless paths the universe could take. The particle could go left or right. The cat could be alive or not. You could have hit snooze or gotten up. But if, upon observation, only one outcome becomes real, what happens to the rest? One answer, perhaps the strangest, perhaps the most haunting, is the many worlds interpretation. It says, nothing disappears. Not the other slit the particle could have taken. Not the other half of the entanglement. Not the other you that stayed in bed. Instead, the universe splits. Every quantum decision spawns a new branch of reality. Each outcome plays out not as an alternative you dreamed about, but as a fully real world. One where the electron turned left. One where the cat lived. One where you called instead of walking away. This is not poetic metaphor. This is a genuine theory, taken seriously by many physicists. No wave function collapse. No probabilities magically vanishing. Just a constantly branching multiverse, eternally growing, where everything that can happen does happen. It's not you chose chocolate instead of vanilla. It's there is now a you who chose chocolate and a you who didn't. The implications are overwhelming. You, as you know yourself, are just one thread in an unfathomably large braid of possibilities. And this branching doesn't just happen when you make big choices. It happens constantly, billions of times per second, everywhere, in every particle, at every quantum fork in the road. Your entire reality could be just one strand of a colossal cosmic braid. Now, is there any way to reach these other worlds? Can you hop sideways and meet the version of you who studied piano? Or move to another city? As far as we know, no. Each branch is decohered from the others. Once split, they don't interact. They're as unreachable as yesterday's dream. But they're not gone. And that's the part that quietly shifts everything. Because in this view, there's no longer a single you moving through time. There's a web of yous, each equally real, each carrying out their own version of reality. And if that sounds a little terrifying, maybe it also sounds freeing, because it means that even your mistakes are just one version of the story. Somewhere else, you said yes. Somewhere else, the door opened. Somewhere else, the version of you who kept going is still going. It's not reincarnation. It's not fantasy. It's branching structure born from quantum math. And perhaps the most radical suggestion? That the universe doesn't need collapse. No observer decides. No wave function ends. It all just continues, in infinite variations. But let's ground this in a feeling. Have you ever stood at a crossroads and felt a presence? Not a person, not a spirit, just a pressure, like something was at stake, like you were standing inside a question. That moment may have been one of many. Maybe the gravity you felt was your mind brushing up against the weight of all those versions, all those branches whispering, choose gently, we're all watching. It makes choice feel sacred, not because it erases the other paths, but because it creates them. And what's even more beautiful, every person you meet is also branching. Every conversation, every sentence, a potential fork. Your story and theirs entangled in the most literal mathematical sense. Let me give you an image. You are standing in a forest, fog curling around the trees. Every step forward splits the path behind you. You don't see it, but each breath births a new trail. Somewhere, the fog parts to reveal a version of you who turned left instead of right. They can't see you either, but you both walk, and the forest keeps growing. That's many worlds. Not fantasy, not wishful thinking. Just a reminder that the quantum universe is endlessly inclusive. It says yes to every path. So tonight, don't worry if you don't know which future to choose. Maybe you don't have to. Maybe you already have somewhere. And all that's left to do is walk your version of the path with curiosity. Let's return to something soft. Closer to home, closer to the body, closer to life itself. Because for all the lab experiments, the laser beams, the vacuum chambers chilled to near absolute zero, quantum physics isn't just about strange particles in distant places. It's also right here inside you. This is the story of quantum biology, a growing field where scientists are beginning to ask, could the strange behavior of particles be essential to life? The answer, surprisingly, is yes. Let's start with something small. Smell. Your nose isn't just a chemical sniffer. Some researchers believe it's a quantum tunneling detector. Here's how it works. A scent molecule enters your nose and binds to a receptor. But instead of just recognizing the shape of the molecule like a key in a lock, your body may be listening for vibrations. Specifically, tiny quantum vibrations of bonds between atoms. If those vibrations match, an electron in the receptor may tunnel through a barrier, triggering the signal of smell. Tunneling in your nose. Then there's photosynthesis, the process by which plants turn light into energy. You might imagine it as a simple, straightforward mechanism. Sunlight hits the chlorophyll, electrons move, energy is stored. But the reality is more elegant, more quantum. Experiments have shown that light energy, after being absorbed, travels through the plant cell in a coherent superposition exploring all possible energy paths simultaneously. It doesn't just pick a route and follow it. It behaves like a quantum particle in a maze, trying every path at once, then settling on the most efficient one. A little burst of quantum computation, right in a leaf. And the story doesn't stop there. Let's look up into the sky and follow the birds. Certain migratory birds, like the European robin, can see Earth's magnetic field, but not with a compass, not with metal, with something stranger. Inside their eyes are proteins called cryptochromes. These molecules seem to support quantum entanglement between pairs of electrons. As the bird moves through the magnetic field, the entangled electrons behave differently depending on orientation. The bird sees this as a visual pattern, like a compass overlaying the world. They don't think about magnetism, they see it. And the secret may be a fleeting burst of quantum coherence in a living cell at room temperature. This was supposed to be impossible. Quantum effects were thought to be too delicate, too easily destroyed by heat and noise. But life has a way of finding the edge, of holding that quantum hum just long enough to turn possibility into survival. Even our sense of direction, our memories, the process of enzymatic reactions, these may all hold faint traces of quantum mechanics, still being investigated, still not fully understood. And what about the brain? This is where things get speculative, but fascinating. Some physicists and neuroscientists have proposed that consciousness itself may depend on quantum effects, on subtle coherence within the brain's neural microtubules. That thought might emerge from wave-like interactions, not just chemical ones. We're far from proof, but the question itself changes how we see the mind. What if consciousness isn't just electrical? What if it's partly quantum? What if awareness emerges, in part, from probability? Now, let's not get ahead of ourselves. Not every mystery is quantum. Not every miracle is a particle joke. But what this growing field suggests is simple and profound. Life is not a layer above physics. Life is physics, cleverly arranged. And sometimes, deeply quantum. It makes sense, doesn't it? After all, the body is built from atoms. Atoms from particles. And those particles follow no classical script. So why should life, and you reading this, breathing softly, drifting, you are made of systems that defy clarity. You are a being built from uncertainty, stabilized just enough to stand upright. It's not chaos, it's structured mystery. Your thoughts flicker, your emotions tunnel. Your instincts may be entangled in ways you'll never measure. So maybe when you smell something nostalgic, when you feel guided without knowing why, when you close your eyes and somehow know where you are, that might not be magic. It might just be physics doing its stranger work. Let me give you an image. A butterfly, wings closed, rests on a leaf. From above, the sun hits its back. A single photon enters the wing, bounces through the cells, tunnels through protein. Somewhere inside, a chemical flips, a signal pulses, and the butterfly opens its wings. Not metaphor, not poetry, just life, built from the logic of shadows. So tonight, rest easy. Your body isn't just obeying rules, it's writing them moment by moment. You are nature's most delicate quantum experiment. And somehow, against all odds, you're working. Let's mix the chaos now. Not the kind you avoid late emails, missed alarms, spilled coffee, but the mathematical kind, the kind that lives on the edge between the predictable and the wild. This is where chaos theory and quantum mechanics begin to stare at each other. Two systems born from different instincts, one deterministic but fragile, the other uncertain but consistent. And when they meet, strange things happen. You've probably heard of the butterfly effect. The idea that a butterfly flapping its wings in Brazil could cause a tornado in Texas. It's a poetic way of saying tiny differences in the starting point of a system can lead to wildly different outcomes. That's classical chaos. Deterministic equations, meaning the future is set by the present, but so sensitive to initial conditions that prediction becomes impossible. A chaotic system isn't random. It just looks random when you don't know the details precisely enough. Now compare that to quantum uncertainty. Here, the unpredictability doesn't come from lack of knowledge. It's baked into the rules. Even if you knew everything that could possibly be known, you'd still get probabilities, not guarantees. A particle may or may not go left. A tunneling electron may appear or not. The randomness is irreducible. So what happens when you take a chaotic system and make it quantum? Welcome to the frontier of quantum chaos. It turns out, even quantum systems governed by wave functions and probabilities can show echoes of classical chaos. You see it in complex atoms, in molecules, in systems where many particles interact. The patterns get twisted. The math starts to shimmer. You get something that feels unpredictable, even though it's quantum at the core. Imagine a droplet of quantum fluid bouncing on a surface. Its path seems random, but map it over time, and strange order appears. Not quite classical, not quite quantum, just structured weirdness. And here's a puzzle. Quantum mechanics, by design, should prevent true chaos. Its equations are linear, smooth. Waves evolve in clean, graceful arcs. So how does chaos sneak in? One answer is decoherence. Once a quantum system interacts with the environment, classical chaos can reappear blurry, yes, but hungry, like a lion slipping in through the back gate. Another answer, quantum systems with many parts can behave chaotically in aggregate. Each piece is simple, but together they become unruly. This matters for quantum computing. It's why keeping qubits coherent is so hard. One bit of entanglement too far, and your clean, orderly system becomes a storm of unintended consequences. But chaos isn't just destruction. It can also be creative. You are a chaotic system. Your brain, billions of neurons firing in complex rhythms. Your breath, your heartbeat, your moods all chaotic, in the mathematical sense, never exactly repeating, sensitive, alive. And maybe, just maybe, your quantum nature rides within that chaos, like a secret undertow. There's a theory still speculative, that consciousness arises from edge of chaos systems, too much order, and you're a robot. Too much randomness, and you're static. But in between, there's flow, creativity, awareness. Maybe your thoughts surf that boundary, too structured to collapse, too wild to predict. Quantum mechanics may be the silent rhythm. Chaos, the beat. Let's imagine it. You drop a pebble into a quiet pond. The ripples move outward, calm and steady. Then you drop 100 pebbles, all at once. Now the surface dances, waves intersect, cancel, amplify. Some ripples form shapes, some vanish. That's what chaos feels like. Not disorder, interference. And maybe life is like that too. 1,000 influences rippling together, genes, memory, experience, dreams, until some patterns rise to the surface. You can't predict them, but you can see them. You can feel the rhythm. Quantum chaos is a reminder that even in the deepest order, there are seeds of unpredictability. And even in wild disorder, patterns wait to be found. So if your life feels tangled, if nothing adds up just right, don't be so quick to label it broken. Maybe you're just in a phase space too large to see clearly. Maybe your trajectory is sensitive to the smallest choice. And maybe that's what makes it beautiful. Let me give you an image. You're in a vast forest. The wind shifts. A single leaf falls not because it had to, but because it could. And somewhere in that falling, the whole forest breathes. You can't trace the cause. You don't need to. The mystery is the rhythm. So tonight, lie back into your own system. Let the noise flow. Let the patterns emerge. You don't have to predict the next beat. Just listen. By now, you've floated through waves, particles, time loops, and invisible fields. You've seen the cat, the slit, the spin, the glitch. You've learned that nothing is really solid, and everything is uncertain, and somehow, it all still works. So let's go all the way out. Let's take the deepest breath and ask the biggest question. What if reality isn't real? More precisely, what if the universe is a simulation? Not a science fiction idea, not a Matrix-style fantasy. A serious, scientific, philosophical question. Could everything you see, space, time, particles, light, even your own self, be part of a vast informational structure? A kind of cosmic code? Because here's the weird thing. The more we study the quantum world, the more it starts to resemble something programmable. Something logical, discrete. Not smooth like clay, but pixelated like a screen. Let's start with the Planck length, the smallest meaningful distance in the universe. Roughly 1.6 times 10 minus 350 1.6 times 10 circumflex, 35 1.6 times 10 minus 35 meters. Below that, space loses meaning. There is no between. It's like the resolution limit of reality. Then there's the speed of light, the ultimate speed limit, as if the universe has a built-in frame rate. Nothing can go faster, no exceptions, not even information. Even energy itself comes in quanta-fixed amounts, like coins, like bits. And when we try to unify general relativity with quantum mechanics, when we look for quantum gravity, some theories propose that space-time itself isn't continuous, but made of tiny loops, cells, or chunks, not unlike pixels. So now the question grows louder. If reality behaves like it's digital, quantized, rule-bound, discrete, could it be a kind of simulation? Nick Bostrom, a philosopher at Oxford, famously proposed that at least one of the following must be true. Civilizations never reach a point where they can simulate universes. They reach that point, but choose not to run simulations. We are almost certainly living in a simulation, because if simulated realities can exist, and if civilizations ever run even a few of them, then statistically, the odds of being in the original reality are very low. Why would this be base reality out of trillions of copies? Now, don't panic. This isn't about alien overlords or secret code behind the moon. It's about looking at the structure of the universe and noticing it acts like a system. It obeys math. It's efficient. It's compressed. Think of how quantum entanglement works, instantaneous correlation across vast distances without energy transfer, like a database lookup, not a signal. Or how wave function collapse only happens when observed, as if rendering is deferred until it's needed to save resources, like a video game engine that loads the world only when the player gets close. Or how particles only exist when measured. Before that, they're probability functions like lines of code waiting to be executed. It's not proof, but it's suggestive. And here's the twist. Even if we are in a simulation, it doesn't make life less meaningful. Because even simulations have real stakes. Even characters made of code feel. Even digital rain can fall on a real face. Plus, simulation or not, we still have to make choices. Still feel joy. Still grow old. Still wonder. There's something freeing about the idea that the universe might be running on information. That you are a pattern, not just a pile of atoms. It means your thoughts aren't just chemical. They're computational. Your identity isn't fixed. It's process. A loop, a script, an ongoing line of code. And maybe, just maybe, the simulation has rules, but not a fixed outcome. Maybe it's a sandbox. Maybe it's running just to see what happens when someone like you shows up. Let me give you an image. You're standing in an ancient temple, high in the mountains. In front of you, a wall covered in symbols, mathematical, elegant. You don't understand them all. But as you run your hand across the stone, the wall shimmers. And the symbols change. The temple isn't static. It responds. You are not just walking through the program. You are writing it as you go. And if reality is a simulation, then that's not a limitation. It's a canvas. So tonight, don't worry about what's behind the curtain. Just breathe. Because even if this is code, you are the poetry it's running. Here we are. After all the flickering particles, the split universes, the vibrating fields and whispers of tunneling electrons, this is where it all settles. Not with a bang, not with a grand reveal, just with a long, slow breath. Because the truth about quantum physics, the most precise, bewildering, successful theory humans have ever constructed, is that it never fully explains what reality is. It just gives us the rules for how the pieces behave. And even those rules shimmer when we get too close. So tonight, we drift not toward understanding, but toward something more subtle. Acceptance. The quantum world doesn't ask to be solved. It asks to be noticed, to be held lightly, to be witnessed with wonder and without expectation. You are a being who evolved on a rocky planet, orbiting a very average star, with a brain made of flesh and sodium and curiosity. And somehow, that brain, your brain, can imagine things it's never seen. You can picture wave functions collapsing. You can visualize particles entangled across galaxies. You can feel, even without equations, that the universe is deeper than logic and larger than language. And in the end, maybe that's what this was all about. Not just science, but the reminder that wonder itself is a form of knowledge, because every theory we visited still leaves unanswered questions. Is time fundamental or emergent? Are there hidden variables? Are we one world or many? We don't know. We might never know. But we do know this. Reality works, even when we don't understand it, even when it contradicts our instincts, even when it feels like a dream made of decimals. Your body functions, the sun shines, molecules bind, photons land in your eyes and make colors. Electrons jitter in your neurons and somehow generate thoughts like the one you're having right now. Even uncertainty produces music. So, let me offer one last image. You are floating not metaphorically but physically. The atoms that make up your body are 99.9999999% empty space, held together by fields, by exclusion, by electrical whispers. Your chair isn't touching you. Your skin isn't solid. The boundary between you and the universe is negotiable. And yet, you feel whole. You feel here, even though you are a wave, even though you are stitched from temporary flickers of borrowed energy, even though you are, in a cosmic sense, a soft ripple in something deeper. So maybe reality isn't made of things. Maybe it's made of relationships, of interactions, of patterns so consistent we mistake them for objects. And maybe that's what you are too. Not a thing, but a pattern, a coherence, a ripple that remembers itself. You came to this story with questions. Maybe you still have them. But you also came with a breath, a heart that beats, a mind that wondered. And that was enough. You don't need to explain the universe to belong in it. You already do. So close your eyes now. Let the probabilities stretch. Let the wave function spread wide again, gentle, uncollapsed. Let yourself rest in the part of the story where answers are less important than peace. You are not behind. You are not broken. You are not alone. You are the echo of a possibility made real. Sleep, ripple. The field is holding you.